Let's take a look at the remaining problems here in the 7.5 homework assignment dealing with partial fraction integration. Number 8 here you can see is the integral of 29x plus 6 divided by x squared times x minus 1 times x minus 3 integrated with respect to x. I'll go ahead and maximize my work here just so you can see it a little bit better. When we're looking at how to work this problem, first thing I did is I said, okay, let's decompose this fraction so that we can integrate each part more easily. So I took the overall fraction and I said, well, since all four, and I did say 4 of these denominators are linear factors, this is x times x minus 1 times x minus 3, then I know that I'm going to have 4 separate fractions, and each numerator is just going to be a constant. I'll have a over the first power of x plus b over the second power of x plus c over the linear factor x minus 1 and plus d over x minus 3. Now, once I have that in there, I can then say, well, let's simplify that expression. I multiply by the least common denominator on both sides. Of course, that leaves me the numerator on the left. On the right, I'll have a times x to the first, one of the x's canceled out, times the other two factors x minus 1 and x minus 3. I'll have b just times the two factors x minus 1 and x minus 3. C, the x minus 1 cancels, but it'll be multiplied by x squared and x minus 3. And finally, d, the factor x minus 3 cancels, it'll be multiplied by x squared and x minus 1. Okay, so now, I'm trying to think of how to solve for variables. Well, I can solve for a if I let x equal 0. When I do that, if I set x equal to 0, my left-hand side is just 6. On the right, a would be multiplied by 0. In fact, I said this would solve for a. It's actually going to solve for b. A is going to be multiplied by 0, so it cancels out. C is multiplied by 0, cancels out. Same thing with d. It would cancel out. However, b, if you plugged in a 0 for x, it's going to be b times -1 times -3. Well, that gives me 3b is equal to 6. Thus, I can see b is equal to 2. Now, I know I could solve for c if I let x equal 1. That's what I did. When I allow x to be 1, my left-hand side is 29 plus 6, or 35. On the right, a would be multiplied by 1, a is multiplied by 0, thus it cancels out. B is multiplied by 0, so it cancels out. And again, d is multiplied by 0, canceling out. The only term that doesn't cancel out and give me a 0 is the factor c. I would have c times 1 times 1 minus 3. That's going to be 1 times -2. I get c times -2. Well, -2c is 35. I can see that the solution for c is -35 over 2. Now I have my answer for b and for c. I can also get my answer for d if I set x equal to 3. Setting x equal to 3 on the left-hand side, 29 times 3 is 87 plus 6 is 93. On the right, a would be multiplied by 0, b is multiplied by 0, c is multiplied by 0. D is going to be multiplied by 3 squared times 3 minus 1. That's 9 times 2. So I get 18d is equal to 93. D would equal 93 over 18. I reduced that down by a factor of 3 to give me 31 over 6. Now, each of those we found just by setting x equal to a certain number that allowed us to solve for it. You have to be a little more clever to solve for the remaining letter a. What I did in that case is I could see that a was going to be a coefficient of x cubed, b is not a coefficient of x cubed, c is a coefficient of x cubed, and d is a coefficient of x cubed. So I look on the left-hand side. The coefficient of x cubed is 0. So the sum of the coefficients of x cubed on the right-hand side must give me a 0. I'll get a, and then my b, I already knew what b was equal to, not b, c. It's a is a coefficient of x cubed, c is a coefficient of x cubed. So plus c became minus 35 over 2, plus D became plus 31 over 6. So now when you solve for A is just going to be 35 over 2 minus 31 over 6. That reduces down to 37 over 3. Okay, so now the original integral, that's this problem, is going to equal the first composed integral. Well, it's going to be the integral of a over x with respect to x. I factor the a out, the 37 over 3, and I get the integral of 1 over x dx plus b. Well, b in this problem was 2. I go ahead and factor the 2 out front. And we know the inside is just going to be x to the negative 2 with respect to x, which we can integrate with our integral power rule. The next term, c. Well, I factor the c out, becomes minus 35 over 2 times the integral of 1 over x plus 1 with respect to x. That's just going to be the natural log of the absolute value of x minus 1 there. That'll be easy. And the last one here, I get plus d. Well, d was a 31 over 6. I factor that 31 over 6 out and get the integral of dx over x minus 3. Now, the first, third, and fourth one, they're just natural logs because the derivative of the denominator is in the numerator. So those are pretty straightforward. The second one's not bad either. You just say, well, the difference in it is you use the power rule. X to the negative 2 is going to become x to the negative 1 divided by negative 1, which we know is better written as negative 1 over x. 2 times negative 1 over x becomes minus 2 over x. That's where that term came from. The rest are the natural logs, just like I said, 37 over 3, natural log the absolute value of x, minus 2 over x, minus 35, natural log of x minus 1, plus 31 over 6, natural log of x minus 3, plus your constant of integration there. Now, final answer there, I should have circled that one, but as you can see, we are done with that one. If I go to Achieve to show you how I inputted that in there, just like what we had right there, and Achieve liked it. For the next question here, number 9, gives me the integral of 21x squared over x plus 1 times x squared plus 1. So for the first time in this assignment, we have an integral in which one of the factors in the denominator is an irreducible quadratic. You cannot factor x squared plus 1. So I know when I'd used the partial fractions, that numerator over that term is going to have to be a linear function. Here's what I did for that. So for number 9 here, this original problem, I say, oh, I'm going to have to break this up and decompose the fraction. 21x squared over x plus 1 times x squared plus 1 is equal to a over the linear factor x plus 1 plus a linear function over that irreducible quadratic. The linear function I'm going to call bx plus c in this problem. Now, just like the other problems, I need to find my letters, my a, my b, and my c. Well, okay, I'll multiply by the least common denominator on each side. The left-hand side becomes 21x squared. The right-hand side, you'll have a times x squared plus 1 plus the group bx plus c times x plus 1 when you multiply by that least common denominator. Now, I can solve for a by letting x equal negative 1. So when I let x equal negative 1, your left-hand side is just 21 times 1 becomes 21. Your right-hand side, the b and the c cancel because they're going to be multiplied by a factor of 0, but the a is going to become negative 1 squared plus 1, so that's 2 times a. So I get 2a is equal to 21, thus a is equal to 21 over 2. Now, what I did for the b term here is I recognized up here that b was going to be a coefficient of an x squared and that c would never be the coefficient of x squared. We already know a is a coefficient of x squared. I looked on the left-hand side and said, well, the coefficient of x squared is 21. The coefficients of x squared on the right are a plus b. So I know a plus b has to equal 21. So b is equal to 21 minus 21 over 2. That gives me b is also 21 over 2. Now, in order to solve for c, what I did is I wanted you to consider the constants on the left-hand side. And you might look at it and say, there is no constant. Right, the constant is 0. Now, what are going to be the constant terms on the right-hand side? In other words, the non-variable term. You would have an ax squared plus a. Well, that plus a, that's a constant. B can never be the coefficient of a constant term because it's tied with the x there. However, this c here, you'd have c times 1, so I'd have a times 1 plus c times 1. Those are going to be my constants on the right-hand side. So now when I solve for c, I can say, well, c is equal to the negative of a, thus c is negative 21 over 2. So I went into my problem and I can say, well, the original integral is these two integrals right here. The first one, I would say, well, the integral of a over x plus 1 with respect to x, I'll factor the a out and say it's 21 over 2, the integral of dx over x plus 1. Automatically, that one's done because it's going to be the natural log of the denominator since the derivative of the denominator is in the numerator. The second one, I go to it and it's going to be a little bit more problematic. I can see that my denominator and numerator differ by 1 degree when I factor out that 21 over 2. So what I did here, plus the integral bx plus c, I went ahead and factored out the coefficient of the x term here, that 21 over 2. When you do that, you'd say, well, that 21 over 2 factors out of both terms. And so that c term, instead of being minus 21 over 2, it just becomes minus 1 up there. Now, when I see that the numerator and denominator inside the fraction differ by 1, automatically I'm thinking there's some natural log involved there. However, if this is simply a natural log, the numerator would have to be 2x because the derivative of the denominator is 2x with respect to x. I can't get a factor of 2x as long as I have two terms up there. But if I separate this integral into two separate integrals, well, then the first term, I could easily multiply that by 2 and divide by 2 on the outside. That's what I've done in the next step here, guys. So I've already integrated the first one, 21 over 2, natural log the absolute value of x plus 1. Then I said, okay, my second one would be this right here. I'm going to ignore the minus 1 for now and just say it's plus 21 over 2 on the integral, or sorry, times the integral of x over x squared plus 1. Now, I know anytime the derivative of the denominator is in the numerator, then I can say it's the natural log, the absolute value of the denominator. Derivative of that denominator is 2x, so I multiplied the numerator by 2, divided by 2 on the outside. Now this one's done. It's going to be 21 over 4 natural log of that denominator. My last one, I had to keep the integral, and I had to keep this second term. So what have I done from here to here? I said, well, since I have that minus, just go ahead and multiply by that negative 1 to the outside instead of plus 21 over 2 on the integral of negative 1 over that denominator. I said, how about I subtract 21 over 2 on the integral of 1 over that denominator. Then as soon as you see the inside of that, you should say, oh, that's by definition my inverse tangent of x. The integral of 1 over x squared plus 1 is the inverse tangent of x. So that last function, by definition, is integrable. The only thing that's slightly tricky here is you do not need the absolute value on the second natural log, simply because x squared plus 1 is always guaranteed to be positive anyway. So, and I've noticed sometimes when you put absolute values on achieve when an absolute value is not necessary, it will actually count your answer wrong. It shouldn't do that, but it has been, I've been noticing. So I would recommend not putting an absolute value on this one, where of course you have to have it here. Final answer, excellent problem there. Now, that was 9. How about we look at 10 here together? In 10, we have the integral of 11 with respect to x over x squared times x squared plus 25. Okay. So when I'm thinking about how to do this problem, I already know my denominator is a linear factor that's repeated with the x squared times an irreducible quadratic with that x squared plus 25. All right. Now, I can go ahead and break that apart, and I know I'm going to have 4 letters in this problem because the degree of that denominator is x to the 4th. So I'm going to have an a, a b, a c, and a d. Well, my a and the b are over this first linear factor. I'll have a over the first power of x plus b over the second power of x. And now that irreducible quadratic factor needs a linear numerator, so we call its numerator cx plus d. Now, once you have this set up, you multiply by the least common denominator. On the left side, I get the numerator. On the right, I'll have a times x to the first times x squared plus 25. I'll have b simply times the irreducible quadratic of x squared plus 25. And I'll have the linear function cx plus d only multiplying the x squared term. Now, what I've went ahead and done from this step to this step is I just tried to simplify a bit further, distributing the x through this group and saying you're going to have c times x cubed and d times x squared over here. Now this lets me see a little bit more clearly what a, b, c, and d are going to be coefficients of on the right-hand side. Now, with that said, I can go ahead and solve for, and it will be actually solving for b by letting x equal 0. If I allow x to equal 0, then my equation is going to become 11 is equal to, a is going to be multiplied by 0, c and d are going to be multiplied by 0, b is not. When you plug a 0 in here, you get b times 25. Well, 25b is 11, so b is 11/25. All right, we have the answer for b. To get to the answer for d, I went ahead and then said, well, think about the coefficients of the x squared terms. A is not a coefficient of x squared, b is, and d is. Well, what's the coefficient of x squared supposed to be? There isn't an x squared on the left-hand side. So I said the coefficient of x squared is supposed to be 0. The sum of b and d would give you the coefficients of x squared on the right-hand side. So I know b plus d must equal 0, thus d is the negative of b. D is going to be negative 11/25. Now, in order to solve for a, I said, well, let's think about the first power of x. Again, there is no x term on the left-hand side, so the coefficient of x is supposed to be 0. The only x term that we have on the right-hand side is 25a, and then b, c, and d. They can't be a coefficient of an x term. So I get 25a would have to be 0. Well, trivially, that gives us a is equal to 0. Similarly, you can say, well, what if you think about the coefficients of x cubed? Yet again, they're supposed to be 0. We already know a is a coefficient of x cubed. C is a coefficient of x cubed. You'd say, well, a plus c is 0. You just solved that a is 0. Well, this is information that tells us c must also be 0. So the only letters that are non-zero are my b and my d. That means that very first partial fraction in this problem is completely irrelevant. You don't have an a over x term, or it'd be 0 over x, which just makes that term disappear. Then you will have this second one. So I can say my integration problem is going to become 11/25 on the integral of x to the negative 2 dx for that second one. And then I have cx plus d, but I know c was 0, so I'll just have a plus d, which is a negative 11/25. Please notice I went ahead and factored that out front and said minus 11/25 on the integral. Now you could have put the dx up in the numerator. I put 1 over the denominator of x squared plus 25 integrated with respect to x. Now at this point, what I did is, just to make it easier, I used the inverse trig integral formula on your table of integrals. You'll see I have it numbered number 6 here. To show you where that came from, I believe I have my table of integrals open here. Let me pull that over. Yeah, there it is. Number 16 on this, you'll see my table of integrals. It says the integral of, and I'll make this a little larger, the integral of du over a squared plus u squared is 1 over a inverse tangent u over a plus c. So I went ahead and used that in this problem, and I can say, well, I just have 1 over x squared plus 5, or sorry, it wasn't x squared plus 5, it was, yeah, x squared plus 25. I was already thinking of the square root. So you can say we're going to have our minus 11 over 25, and then this integral by number 16 is equal to 1 over the square root of this number, 1 over 5, inverse tangent of x over 5. That's applying that integral formula number 16 to this second integral, plus our constant of integration. After that, I distributed the 11 over 25 through that term to get my minus 11 over 125 inverse tangent of x over 5 plus c. Please also keep in mind that first one, it would have integrated to be x to the negative 1 over negative 1, which is why this sign out here in front changed from a positive to a negative. Negative 11 over 25, x to the negative 1 becomes x to the positive 1 in that denominator. And now when you see this problem on Achieve, the number 10, you can see exactly what I entered in there and how it matches what we just discussed. Now for the absolute most gorgeous problem in this entire assignment, and possibly for the entire class, I really like number 11. Now, we won't get into any more rigorous problems than this one. Could have we got an even more gorgeous problem than number 11? You could have. I could have had 2 irreducible quadratic factors in that denominator being squared, and that would have made this long problem even longer. But this one is fine as far as difficulty level. A lot of students would find this one extremely challenging. Let me see if I can explain it here to you. So I took the rest of the work on this page and an entire other page of work to do this one problem. So this one's going to take a while to explain. We're starting off with this rather innocent looking original integral here, 75 over x times the irreducible quadratic, x squared plus 2x plus 5, quantity squared. Okay, so I had to use the method of partial fractions, a over the linear factor x, plus bx plus c over the first power of this irreducible quadratic, plus dx plus e over the second power of that irreducible quadratic. Again, you should have known from the very onset of the problem that you would need an A, a B, a C, a D, and an E in this problem. Why? Because you're going to have 5 letters to account for the degree 5 of x in that denominator. Now, as I try to simplify here, I'm multiplying by the least common denominator throughout the entire equation. On the left-hand 5, I just have 75. I'll have a times that irreducible quadratic factor squared. I'll have bx plus c times x times the irreducible quadratic, plus dx plus e, simply just times x. Now, what I did to try to simplify this is I went out and I distributed x squared plus 2x plus 5 times x squared plus 2x plus 5. I did it on another sheet of paper as to not make this problem even longer. And when I multiplied that trinomial by itself and simplified, I got a times this expression. So I have 75 is equal to a times x to the 4th plus 4x cubed plus 14x squared plus 20x plus 25. Now I needed to see what b is in front of. Notice you have a bx times x times the irreducible quadratic. So that means b is going to be multiplied by every term in here times x squared. That's precisely what I did. And then c is multiplied by x in this group, so it's multiplied by that group times x. So I get c times x cubed plus 2x to the 2nd plus 5x. d is going to be multiplied by x squared, and e is only multiplied by x. Now that I get that in there, I then need to try to somehow figure out what are these values of a, b, c, d, and e. So the first one, I can figure out a by setting x equal to 0. That's precisely what I did. When x is 0, your left-hand side, still 75. Your right-hand side, you would have B and C multiplied by a factor of 0, D and E multiplied by a factor of 0. The A, whether you look at it up here or down here, you can see A is just going to be multiplied by 25. Here it'd be 5 squared, here 25. 25A is 75, thus A is 3. Now that's the only one I can solve by setting x equal to some number, because there's no value of x that will make either of these two denominators equal to 0. So then I can say, well, all right, let's do some logical thinking then. I think about the coefficients of x to the fourth in the problem. Left-hand side, the coefficient of x to the fourth is clearly 0. There is no x to the fourth term. On the right, you know A is a coefficient of x to the fourth, so is B. None other are. So I know A plus B has to equal 0. Thus, B is the negative of A, B is negative 3. Now let's think about the coefficients of x cubed. Again, that's 0 on the left-hand side. On the right, I know 4a is a coefficient of x cubed. I know 2b is a coefficient of x cubed. And c is a coefficient of x cubed. That's where this equation came from. And then you know a is 3, so you're going to have 12. B is negative 3, so that's going to be minus 6. Plus c has to equal 0. That allowed me to go in and see that c had to be negative 6. All right, now I have A, B, and C. How about if I think about the coefficients of x squared? Again, on the left-hand side, there isn't an x squared term, so its coefficient is 0. Coefficients of x squared on the right, you'll have 14a, you'll have plus 5b, plus 2c, plus d. That's where this equation came from. Then I multiplied through, I said 14a is just going to be 42, plus 5b is going to be minus 15, plus 2c is going to be minus 12, and then I had to solve for d. And I said, well, 42 minus 15 minus 12 minus another 15 would be 0, so I said, well, d has to be negative 15 then. Now, in order to solve for the final letter E, I just looked at the coefficients of x. I knew that the coefficient of x on the left was 0. On the right, I would have 20a, and then b is not a coefficient of x. C is. 5c would be a coefficient, and then, of course, e. You have 20a, that's going to be 60, 20 times 3, plus 5c, that's 5 times negative 6, minus 30, plus e. So then 60 minus 30 plus e is 0. E is going to have to be another negative 30. So now I've solved for all of my values in there. I want to rewrite my integral. And then there's still so much work to do even after this. This is just the algebraic setup. So the original integral is equal to, the integral of a over x becomes 3 times the integral of 1 over x dx. I know that one's easy. It's just 3 natural log the absolute value of x. Ding, ding, done. The next one here. Plus the integral of bx plus c. Well, here's my b, here's my c. I went ahead and I factored out that negative 3, and I said minus 3. And when I factor out that negative 3, your first term's just going to be x. Your second term's negative 6 divided by negative 3, or in other words, plus 2, all over that denominator. And then my last one, I did the same thing here. I said, well, I know my d is a negative 15. So how about I just go ahead and factor out that negative 15, so I just have an x on the inside. Minus 15 on the integral of x, and then the second term, it would have been minus 30. Well, minus 30 divided by a negative 15 leaves me a plus 2 there as well. And so I get x plus 2 over that irreducible quadratic factor in the denominator squared, integrated with respect to x. Now, I knew as soon as I was looking at this, well, the first one is easily integrable. The second one's going to require some more work, quite a bit more work. And the third one's going to require a lot more work. So anytime you have a problem like that, it is common notation to do some kind of subscript, well, not subscripts, but identifiers in the problem. Like, I'm going to call this subproblem A and this subproblem B. And now you'll see on the next page, I said, well, let's look at that subproblem A and work that out. And then I looked at the subproblem B to work it out. So now, the subproblem A part, where I have the integral of x plus 2 over x squared plus 2x plus 5. The first thing I want you to remember is anytime the degree of the numerator and denominator differ by 1, you've got a natural log in that problem somewhere. So I'm thinking, well, if it were the natural log of that denominator, my numerator would need to be 2x plus 2. And you look at it and you say, but it's not 2x plus 2. I can make it that though. All I have to do is go in and multiply my numerator by 2 and divide by 2 on the outside. Now I know what you're thinking. You're thinking, well, you didn't make it 2x plus 2, you made it 2x plus 4. Absolutely, I did. Okay, how am I going to handle that? Then I'll say, well, it's 1/2 the integral 2x plus 2 over that denominator. Please notice, why am I doing this? I am forcing what I know will be integrated as the natural log of that denominator. And I didn't need the absolute, I didn't need the absolute value because that denominator is guaranteed to be positive. So this part I forced in there so I knew I could integrate it. But then you say, well, you didn't have 2x plus 2 in that numerator, you had 2x plus 4. Well, then I need to account for plus 2 more in that numerator. I did that right over here. Now, in this step, we know that the 1/2 would have been in front of both of these integrals because the 1/2 would have to distribute to any integrals that I separate up. Well, hopefully you see what I've done here. I've taken that 2 that would have been inside here, multiplied it on the outside, 1/2 times 2 just canceled out, and I have plus 1 times the integral of 1 over this denominator. Now, that is what I need to work with. This first one, I can already integrate. The second one, I need to put in a better format. Here's how I got the better format. Again, I would like to work towards where I can get it in the format of that inverse tangent function where I have 1 over a variable squared plus a constant squared is going to be 1 over the square root of that constant inverse tangent of the variable over that constant, the square root of that constant. Here's how I do that. I complete the square on the denominator. X squared plus 2x plus 5. I say, well, I know that that 5 is not what I need for a perfect square because it's not a perfect square. So I went ahead and separated it. Now, this 1 was not there previously. I just had x squared plus 2x. And then I thought, well, what do I need to add to that? If you remember your perfect square trinomials, it is always, the term you need here is always half of b squared. So I said, in order for that to be a perfect square trinomial, I need half of 2, which is 1, and then square it. I need a 1 in there. So I added 1 on the inside, subtracted 1 on the outside. So this is equivalent to, this trinomial is better written as x plus 1 quantity squared. And then on the outside, you would have a plus 4. Now, I promise you, this, if you squared out x plus 1 squared, added a 4, you'd get that back. Of course, it's an equality. However, this is so much better inside of our integral. So I'll replace this with what it's equal to in perfect square format. And then as soon as I see 1 over a variable squared plus a constant squared, I'm thinking, yes, that is formula number 16 that I just showed you on our table of integrals. Does it matter that it's the group x plus 1 as opposed to just the x squared term in there? Not at all. So our table of integrals, which I'll bring over here to the end, there we go. Number 16 says if you have du over the over a squared plus u squared, then the integral of that is 1 over a inverse tangent u over a plus c. Well, this is the exact same thing as that, except in the place of u, I need to use the group x plus 1. So I can say, well, then this is going to be 1 over the square root of this number, 1 over the root of 4 inverse tangent of x plus 1 divided by the root of 4 plus your constant of integration. Now, I'd already integrated the first term there to the natural log. That 16 is how I did this one right here. Now, I'm done with A. Let's look at the other part that I called B in this one, and this is going to take even longer, but it's gorgeous. I have x plus 2 over the group x squared plus 2x plus 5 squared. Yet again, I would like to try to get in that numerator the derivative of what's inside the denominator, because then I know substitution would be helpful. So I'd like to get that numerator to be 2x plus 2. Just like I did up here, I'd say, well, I'm going to have to multiply by 2 on the inside, divide by 2 on the outside. So I get 1/2 times, now this would have been 2x plus 4 on the inside. I left it 2x plus 2 because my remainder plus 2 is over here, and I took that 2 to the outside to get rid of the 1/2. So that's where this numerator come from here. It would have been a 2 and a 1/2 on the outside. You have to cancel those out to just get a 1 up there. And so now we look at this and say, what are we going to do here? Please also notice I left this denominator as the irreducible quadratic factor squared. I went ahead and put the exact same denominator, but I put it in the perfect square format over here. Okay, now the reason I left it in this format over here is because this is the one where I wanted to use substitution and just say, why don't I just let u equal what's inside of that group to a power? Let u equal x squared plus 2x plus 5. Well, then du would be 2x plus 2 with respect to x. I know that this is just going to simplify to be the 1/2 the integral of u to the negative 2 du. That's what I have right here. And I know once I get to that, that'll be easy to integrate. The second portion over here, not as easy, but probably more fun. As soon as you recognize you have a variable squared plus a constant squared, you can say, that'd be a tangent substitution. So in this case, what's taking the place of the variable is the group x plus 1. I'm going to say, then let's let that group x plus 1 equal a tangent theta, where a is the square root of this number, 2 tangent theta. So x plus 1 is 2 tangent theta. Take the derivative of the left-hand side, you get dx. Derivative of the right, 2 secant squared theta d theta. Now I go back and I can show, well, x squared plus 4 quantity squared, what is that going to equal? X squared plus 1, x plus 1 quantity squared is equal to 4 tangent squared theta. Then we have plus 4. So on the inside, this could factor to be 4 times tangent squared plus 1. That's going to be 4 secant squared on the inside. The 4 squared becomes 16. The secant squared becomes secant to the 4th. So now I go back to my problem and I can say, all right, this first part is just u to the negative 2 du. That's going to be easy to integrate. The second part, the dx is in the numerator, so I know my numerator is going to be 2 secant squared theta d theta. My denominator is going to be the group, which I've shown is 16 secant to the 4th theta. Now, as I go from this to the next step, I just looked at this one and said, okay, that's going to be u to the negative 1 divided by negative 1. When I divide by negative 1, it's going to change the sign of this 1/2 to a negative 1/2, and then I would have u to the negative 1, means that group u is going to be to the positive 1 in the denominator, and I just went ahead and substituted x squared plus 2x plus 5 back in the place of u. I'm done with the first part, or the first integral of b. The second one, the 2 over 16 factors out to 1 over 8, and I would have left a secant squared in the denominator, which we know is the same thing as cosine squared in the numerator. Now, in order to do that, though, I can say, well, I can't integrate the power, the second power of the cosine function, so I'll use my power reduction formula that says cosine squared theta is equal to 1/2 times the group 1 plus the cosine of 2 theta. And that's what I've done here. I've just rewrote my first term. The second term, the 1/2, came out and multiplied the 1 over 8 to give me 1 over 16 on the integral of 1 plus the cosine of twice the angle integrated with respect to theta. Now, once we do all of the integration, our first term, again, just stays along. The second term is going to be 1/16 times theta plus the sine of 2 theta over 2 plus your constant of integration. In this step, I went ahead and said, well, we know that the sine of 2 theta is 2 sine theta cosine theta. This 2 and the 2 in the denominator would cancel. So that's just going to be theta plus sine theta cosine theta on the inside. Now, the way I went from this to the next step, I had to be thinking about a trig triangle. That's how you substitute back in x in terms of theta. So my trigonometric substitution said that x plus 1 is equal to 2 tangent theta, which means that the tangent of theta is equal to x plus 1 over 2. Now, that means within a right triangle, x plus 1 is the side opposite theta, 2 is the side adjacent to theta, which then means your hypotenuse is the square root of this side squared plus this side squared, which would take us back to this right here, x plus 1 squared plus 4. I just went ahead and put what that's equivalent to, the x squared plus 2x plus 5. Okay, now I go back to my problem and I can say, well, we can't forget this first part of b that we've already integrated is right here. Now we're going to have 1/16 times the group, theta. Well, what is theta? Tangent of theta is x plus 1 over 2. So theta is the inverse tangent of x plus 1 over 2. That's where that came from. And then plus the sine of theta, opposite over hypotenuse, times the cosine of theta, adjacent over hypotenuse. That's where those two came from, plus your constant of integration. So now, at this point, it's just simplifying out. I had to go in and say, all right, all of this part on this page, it was just to do the part A and B from what I have here. I'll have the overall integral is equal to the integral of this first term, which was ridiculously easy. That's just 3 natural log of the absolute value of x. And then we had minus 3 times the answer I got for A. Well, the answer I got for A is right up here. It's just these two terms. I can leave the constant integration for the end. So you can say, well, that's where he got that right there, minus 3 times A. And then it was minus 15 times the answer I got for B. So minus 15 times all of this answer I got for B here, you'll see there's the first term, and then I have the 1/16 inverse tangent of x plus 1 over 2. And then for this last term here, I said, well, 2 over 16 reduces down to 1 over 8. So I had plus x plus 1, the 2 canceled out, over 8. And then these two square roots multiplied just to give me the group x squared plus 2x plus 5, plus your constant integration. All right, now when I cleaned up this answer to get to my very last step, here's what I did. I said, well, I only have 1 natural log of x term. I'll just bring it down, 3 natural log of x. And then this second term, which I do not need the absolute value on because this quadratic is guaranteed to be positive. All it is, remember, it's this right here. It's a parabola that's been shifted 1 unit left and 4 units up. So it has a minimum y value of 4 when x is -1, meaning it can never be negative. So please don't put an absolute value around it. Achieve might count it wrong. But those two terms fall out pretty directly. Then I said, well, please notice you've got this inverse tangent function and this inverse tangent function. This would give me minus 3 over 2 inverse tangent of x plus 1 over 2. This would give me minus 15 over 16 inverse tangent of x plus 1 over 2. I combined those two to give me minus 39 over 16 inverse tangent of x plus 1 over 2. And then where this term right here came from is I looked at these two terms in there and I said, hey, I pretty much have the same denominator there. All I would need to do is multiply this one by 4 over 4 to get a common denominator with this one. When I do, this becomes -4 over 8 times the irreducible quadratic. And I get -4 plus x plus 1. Well, x plus 1 plus a -4 gives me x minus 3. That's where that x minus 3 came from. And I'm still multiplying that group by minus 15. So I said minus 15 times x plus 3 over that common denominator of 8 times x squared plus 2x plus 5 plus the constant of integration. And if you're like me, you will thoroughly enjoy doing that problem. That's one of my favorite problems that I've truly seen as a great one. Not too hard. I mean, hard enough, but not incredibly hard. And you can see where I entered that answer into Achieve and achieved liked that answer. Now for number 12, it's very anticlimactic and not nearly as fun as the previous few problems. When I'm looking at this one with you, and I think I can even make it smaller, it didn't take a whole lot of room. So what I did here, it's the integral of secant squared theta over tangent squared theta minus 484 integrated with respect to theta. Okay, so in order to work this problem, what I did, and I followed their directions there, it says evaluate the integral by using substitution first. Well, the clear substitution in this problem is to let u equal the tangent of theta. If you do that, du is secant squared theta d theta, so all of that numerator cancels and just becomes du. Your denominator is going to become u squared minus 484. At that point, you're supposed to recognize perfect square minus a perfect square. A squared minus b squared is a plus b times a minus b. Well, okay, u squared minus this is 22 squared becomes u minus 22 times u plus 22. Now, I went ahead and showed my algebra down here, and I said, well, I'm going to need to simplify 1 over u minus 22 times u plus 22 into its simpler partial fractions. A over the linear factor u minus 22 plus b over the linear factor u plus 22. So I get 1 is equal to a times u plus 22 plus b times u minus 22 after multiplying by the common denominator on both sides. After doing that, you can say, well, you should be able to solve for a by letting u equal 22. If you let u equal 22, your left-hand side is still 1. Your right-hand side, b would be multiplied by 0, but a is multiplied by 44. You get 44a is 1, thus a is 1/44. Similarly, if you let u equal negative 22, a gets multiplied by 0, b gets multiplied by negative 44, making b equal to negative 1 over 44. So now we get our answers for a and b. B is just the negative of a. And then we can go back into our problem and say, all right, this is going to become the integral of a over u minus 22, which is going to be 1 over 44. The a gets factored out, du over u minus 22. And then instead of plus, since b is negative, I get minus 1 over 44 du over u plus 22. Now, in both cases, the derivative of the denominator is in the numerator, so it's just the natural log of the absolute value of each denominator. And then you can just say, well, after that, you substitute back in u, you'd have tangent theta. You get 1 over 44 natural log of tangent theta minus 22, minus 1 over 44 natural log of tangent theta plus 22 plus c, which that answer is fine. But anytime I have the same coefficients, I prefer to go ahead and condense those two. I don't see any reason why you wouldn't. And I'll just say this is 1 over 44 natural log of u minus 22, and then this minus just means that term goes in the denominator, u plus 22, which of course u is tangent theta, so I get the tangent theta plus 22 in the denominator, plus your glorious constant of integration. And you can see that's precisely how I entered it in to Achieve, and Achieve liked that answer. So by far the most fun problem in here was number 11. Let me know if you're struggling with that. Please, if you are struggling with it, send me your work so I can try to see where you're going wrong in the problem, and I can probably help you out with that. Otherwise, I hope you're enjoying working these problems. This is a absolutely fun section, one of my favorite of the semester. Now, the next section we're doing 7.6, it's going to combine these techniques of integration. So we're going to have substitution, integration by parts, trig integrals, trig substitution integrals, and our partial fractions all within the same section. So it becomes some fun stuff too.